Thank you, Chairman, for your kind introduction. And also like to thank all of the audience to stick to this session. So today, I will show you some of our recent thinking about how we do some de novo design for nanomedicine. And I also present this on behalf of Professor Yuliang Zhao. So he is our director, deputy director of our National Center for Nanoscience Technology. I think we hear a lot of, in this meeting, we hear a lot of interesting talks talking about how we have different strategies to inhibit tumor cells and also try to cure this as a very deadly disease. But we also know that there's a very early hypothesis, I think back to the 18th century, and people already proposed that tumor actually not single tumor cells, but they also have some surrounding cells and stromal cells, and they together its organ is not a single cells. So all of the current mechanism only targeting about tumor cells, but recent study, I think more and more evidence suggests that if we have the way to regulate the surrounding cells, for example, fibroblasts, endocellular cells, and also immune cells, probably will have better way to control the cell metastasis and also fast growth. And also we know from a lot of cases, we know that if you directly kill cancer cells, basically give the selection pressure, whatever the methods you used, you probably select very malignant tumor cells, let them be more aggressive. And so I think since 2003, almost 10 years, I think, we work with a new type of nanomedicine, we called it. So basically it's such like small nanoparticles. It's based on the fluorine structures, and we also have some encapsulated gadolinium inside, and we have the surface modification. So basically, it's a series of different gadolinium particles, different modification, and different numbers of surface functional groups. But why we get into this field is really by accident. Initially we want to develop some gadolinium fluorines, basically for use as a MRI contra-agent, because we know fluorines have a good signal if we can use it, either with chelators or with some other nanoparticles. So this somehow we start work on this gadolinium nanoparticles. And so here we saw that basic structures, it's just like the football is a ball. And when you have chance to insert something inside, and this is the metal can have interactions with the surface functional groups. So together, it's a new type of structure, nanostructure. And I think the most important thing for us is how to control the nanosurface chemistry of such structure, because we know that the uniqueness of the structure is you have the encapsulated metals and inorganic elements, but we also have surface functionalization strategies. So sometimes you can introduce hydroxyl groups, and also you have to control numbers, how many you want. Because from our current study, we know that the more hydroxyl groups introduced on the surface, basically a decreased stability of such a nanostructure. And so our past 10-year study shows that this structure have a very effective effectiveness in terms of inhibition of tumor growth and also the tumor metastasis. I show you some our data. So initially we took several like tumor models commonly used in our lab. So for example, the breast cancer model and also liver cancer models. And what we found that when we intravenously injected such structure, we see that very dramatic inhibit tumor growth. And if you see the images, it's very dramatic, shows that it's indeed can inhibit tumor growth. And I think more interestingly, we consistently found that in different tumor models, that actually not only for the primary tumor cells, but also for the metabolite, for the tumor cells inhibit metastasis. And so, for example, this is a pancreatic tumor model 2. We also see that such effects can be observed by the so-called environmental SEM to see the surface of the blood vessels. So basically, you see that a lot of blood vessels in the untreated groups, but getting very less blood vessels in the surface of the tumor. And again, that's another model. This is a human breast cancer model, and it have a very dramatic lung metastasis. And if you will compare, for example, in the endpoint, we take out the lung tissue, we see that this is the cured, and this is a lot of new lung metastasis sites here. And also this shows that the size and the weight of the lung. And this, we also follow this process by looking at the fluorescence emitted by these tumor cells. So they all together shows that in different models we can see these highly inhibit tumor cells metastasis, and they basically we see that blocked tissue invasion. So far I show you some evidence that the new type of nanoparticles can dramatically inhibit tumor growth and metastasis. But more interestingly, we didn't see any direct effect to kill tumor cancer cells or no systemic toxicity in vivo. This is totally against the current method used in the clinic or in the research. So we took different tumor cell lines, for example, pancreatic cell lines and lung liver cell lines, and also breast cancer cell lines. Whatever we use, the concentration, we didn't see any effect on cell viability. But compared to other methods and to commonly used chemotherapy drugs, they also very dose-dependent inhibition. But in our case, we never see whatever the concentration is. There's no effect, dramatic effects on cell viability. And furthermore, we also look for the systemic toxicity. For example, we never see the body weight changes, even though long term of time. And compared to the chemotherapy drugs, you always see that dramatic decrease about tumor-laden mice weight. And also we did historical evaluation. We never see clear damage to either spleen, liver, kidney, and also other main organs. So far I show you a very interesting observation that without direct interact with tumor cells, but we see such nanoparticles can really inhibit tumor growth. So then what happened? What's the mechanism behind that? So I think maybe that's a lot of interest, a lot of people. So again, this is the scheme shows that other than tumor cells, whatever these benign and malignant, they also have their surrounding environment, microenvironment. And all of these, according to current knowledge, either the somal cells and also the non-cell components, they can dramatically inhibit, interact with tumor cells to cultivate them to be tumor cells. And so we first start the angiogenesis process because certainly we know that there's many like blockbuster drugs already developed based on this strategy. So we see if these new nanoparticles can basically inhibit or interact with the angiogenesis process. And we found that compared to the control groups, so the gadolinium nanoparticle treatment can dramatically inhibit the tumor vessels, the density and blood fusion, all of this very essential process for to deliver either energy or nutrients to tumor cells. And when we look for the all of the key players in the tumor angiogenesis, and we see that a lot of them just downregulated. And furthermore, if you look at the images by various methods, you always find that nanoparticle treatment can dramatically decrease the blood supply for the tumor. So basically, you cut off the nutrition channels to tumors. And there's another very dramatic sort of pathological observations. We keep looking, find out that when these nanoparticles treat the tumors, they always shows that formation of fibrosis-like structure. More presently, we can see that here. So this is a control tissue, like the control group without treatment. So you see tumor tissues very much of the main mass, and surrounding tissues less. But if you treat with the nanoparticles, you see very dense fibrosis-like structures grow up on the surface, and more clearly from other images. So this just sort of observation already been reported in the literature. So whenever you have a foreign invasion of things, the tissue have the function to encapsulate them in a encapsulated structure. And this is exactly looks like that. So we then go a little bit further to see what's happened for these people well known like MMP family members. Basically, they are the protease can degrade the various of collagens of those things to make open the door for the tumor cells to metastasis to other places. And we see that it's a sort of a dose-dependent decrease about MMP2 expression and MMP9 expression. So this is sort of very broad targets against this our current understanding about normally a biological active compounds. Most likely they have only one or maybe two confirmed targets. But for our case, it's always see that you have multiple targets, not only for one molecular target. And so furthermore, we just want to know why such things happen, because certainly according to the traditional key and keyhole theory in the biology systems, you always have a ligand and a receptor. They can work together very specifically. And then we use some molecular dynamic simulation to figure out what's happening for these nanoparticles, because they saw that so far they have a lot of multiple targets. And we found out actually this is not as the traditionally understanding about key and keyhole relationship. And all of these so-called weak interactions between nanoparticles and their targets work together. For example, hydrogen bond and also the static interactions. They all work together to let the nanoparticles interact with multiple cellular targets. So this is really something is out of the scope of traditional biology studies. So then after we show you some of these interesting observations, so we propose some new strategies. So traditionally, I think most of the strategies using the poison strategy to either kill the tumor cells or inhibit them proliferation. That's the most of people try to work with the tumors. But if we work with the new type of nanostructures, they basically can form a very dense fibrosis tissue around the tumor cells. So basically, this such structure can be used as a sort of a prison strategy. They can just hold the tumor there and not let them fast proliferation and get invasion to other local tissues. And this is the case for local. If you block the tumors surrounding tissues, basically to block the, the induced tumor cells to sort of a stage of starvation and induce the tumor cells go to the apoptosis or necrosis. And the same thing, if you block the blood supply, you have the similar effects. So just to sum up what I show you today, so our study basically support the very old hypothesis that it's the seed and soil theory for the tumor. So as long as we can control the tumor surrounding environment, microenvironment, we have the power to control the tumor, the fate of tumor. So we know that a lot of players around. So today I saw two of them. One is the fibroblasts associated with fibrosis structures. We also show you the angiogenesis. But certainly we are not sure that's the only mechanism we found about nanoparticles. But indeed, we think the altogether it's a new way to shift our current understanding how to cure cancer. And to push forward our current study, we want to go some preclinical investigation, because so far the most limiting factors for us is the making enough drug to treat, to do some preclinical study. So then we think about want to make a manufacturing facilities to make such very expensive nano drugs. So then we start in 2012 in our institute. We set up a dedicated facility room just to make for make enough amount of such structure can be used for the preclinical and clinical study. And so now the whole system already been set up, and it's just running. And now I think the capacity to make this gadolinium fluorine structures we can count about almost let's say something from 0.1 to 1 gram per year. But it's good enough for us as a pilot plant to make enough amount of such structure. And so this is my last slide. So I just want to convince you that today, during the past 10 years, our study showed that actually compared to a traditional way to cure cancer, we can have a de novo design strategy for nanomedicine. The totally nanomedicine is not similar as our previously well-known molecular medicine. Totally, they are based on the structure specific functionality of particles. And so we all know that this is poison cell strategy have a lot of problems. So how about we shift to this new diagram by, for example, block the blood supply and the nutrition supply, and to block the connections between tumor cells with their microenvironment. So we can sort of have this prison cell strategy. So far I think our evidence show that this is a very promising direction, but certainly there are a lot of long way to go, because it's really a challenge for our understanding the current landscape of tumor biology and also therapy. So finally, I would like to thank our colleagues. They contribute in the past 10 years to have this study done. There's a lot of people contribute on different directions. And we also thank for our funding agencies to support our study. In the past 10 years, we spent a lot of efforts to keep this progress going. But so far, we think we are very happy to see what we've done. Thank you very much. So, yeah.
Thank you very much for this interesting talk, showing from the beginning up to the, let me say, pilot production at least.
Yeah.
Do you have questions to this presentation? There is one, at least.
Thank you very much for your presentation. And I have one question for you about the safety of gadolinium-based nanocell systems, because It is well known that gadolinium contrast agents have, in a certain patients, when the gadolinium remain for a long time into the body, they generate or can generate so-called nephrogenic fibrosis syndrome, nephrogenic fibrotic syndrome.
Mm-hmm.
So it is something like what you are looking for into the tumor, right? So there is a sort of fibrotic fibrosis triggering coming from gadolinium that probably in the contrast agent case is produced by gadolinium phosphate, which is a colloidal system that is produced by the just the elimination of the gadolinium from the cage of the chelate. Now, why you think that in your case there is not this kind of risk associated in the use of your system?
Thank you very much. I think that's a very stimulating question for me. I think as far as I know, the gadolinium-based counteragent. So I think the major problem, as you mentioned, that probably is due to the free-form, we call it free-form gadolinium released from their chelators. So probably that's the main mechanism for the toxicity you observed. But for this case, I think in our case, the difference is that the gadolinium, ideally, they always keep inside the cage. So whatever they interact is with their surrounding carbons or their surface functionalized groups. Because one of the criteria we want to control the chemistry is that make the cage very stable. As I mentioned at the early beginning, whenever you modify the surface with different numbers of groups or group numbers, for example, hydroxyl groups, so there is a trade-off. When you increase that hydroxyl group, for example, you increase the interaction with the sort of the efficacy, but you also decrease the stability. So in our case, we keep that structure, the HO groups under 22, so it's the most stable stage. So hopefully, in that case, it makes the structure very stable. So no gadolinium release to the tissue. So I think that's a difference compared to our system with the current chelator-based gadolinium counteragent.
Yeah, even if the basic idea is that it's gadolinium phosphate, colloidal gadolinium phosphate that can trigger this kind of syndrome. So it's not the free gadolinium, right? Because the gadolinium is not stable in blood, just precipitate immediately after the release from chelate and generate colloidal phosphate, and then this colloidal phosphate can accumulate into the tissues in many different ways. Of course, your system is different, but I think maybe very important to look at this kind of safety issue, and also looking at possible accumulation of gadolinium in the bones. Have you ever seen it? Because gadolinium generally accumulate into the bone if there is some release during the usage.
Okay, thank you for the comments. So, yeah, it's worth to look at that. Yeah. Thank you.
Starvation tend to encourage autophagy. So once you enhance starvation, but whatever mean, you might be encouraging autophagy, and it's found now that cancer cells plays fantastically with autophagy, maintain themselves. Any comments or any observation here?
Yeah, that's very good another comment too. I think you're talking about the autophagy induction by starvation. I think it's well known, but most likely that's at the cellular level observation. Probably, I'm not quite sure. I found very strong evidence that in tissue levels you see that starvation induce autophagy. Maybe, but also can be some other like type of cell death induced, like necrosis, apoptosis. But definitely that was to have a look at that. We haven't really go that far to see if that really our system see the tumor cells autophagy. Yeah. but very hot field in recent years. Yeah.
Okay. Yeah. Thank the speaker again. Yeah. For this work. Now I like to